Hi everyone. Welcome back to Dave's Math channel. Today I'm going to do another video in my series on logic, and this is another logical paradox known as a liar paradox. Probably the simplest one. So it's really just a statement, I am lying. If somebody says I am lying, that can't either be true or false if you think about it, because if they were lying, they'd be telling the truth, and if they were telling the truth, they'd be lying. So that can't be either true or false. And this paradox actually, there's different forms of it. I mean, sometimes an easier way to think about it mathematically. Sometimes people just say this sentence is false, or you can call sentence A the sentence that says sentence A is false. And, it's the same thing, obviously, because the sentence is saying that it's a lie, basically. So, and you get the same contradiction from it. And, you can be a little more subtle about it. It doesn't have to be one sentence. You can have two sentences or a chain of sentences. For instance, you can have two sentences called A and B, where A says B is true and B says A is false. And if you try to assign consistent truth values to both A and B, you can't do it. It just because A says B is true, B says A is false. If you assume they're both true, then you conclude that A is false. You get a contradiction. If you assume A is false, then that means that B has to be false too. But B says that A is true, so that means A has to be. You get a contradiction either way. So anyway, and you can do as long a loop as you want. So those are kind of sort of variations of a liar paradox, um, if you look at where this originated from, it was actually an ancient Cretan named Epimenides who came up with this paradox. It's also called the Epimenides paradox. And the way he said it, he was from Crete, so he made this statement that all Cretans are liars. And you can see that that statement implies that he's a liar since he's a Cretan. So it basically amounts to the same paradox, the liar paradox. And I think the first person to sort of analyze this as a logical paradox was the English academic Thomas Fowler, so in 1869. And so there's several different ways you can resolve the liar paradox. And I guess some of the early ones in 1933, there was the Polish logician Alfred Tarski who defined a true sentence as a sentence that says something else about the world, not just about itself. I mean, ultimately, the problem with the liar paradox and a lot of other logical paradoxes like this stems from self-reference. Last video I made was on the Berry paradox, which was another paradox involving self-reference. So there's a lot of paradoxes. There's a lot of logical paradoxes that ultimately stem from self-reference, and you have to define things very, very clearly and precisely, and you have to establish some very rigid rules in order to avoid these paradoxes. So there were a couple attempts to do so. 1930, Alfred Tarski did this. He said that that a sentence can't be the truth of a sentence doesn't stem from anything it says about itself. It stems from something it says about something else in the world. So if you say that, and I guess that applies to chains of sentences, they can't ultimately refer back to themselves. Um, then you do avoid this paradox because then the statement "I am lying" or the sentence is false. That can't be true because it doesn't say anything. It's really a sentence that just says something about itself and it doesn't say anything else. So that I guess that would be, I guess you could say it's neither true nor false, but it's certainly not true because it doesn't add any information to the world. So that was his way of kind of resolving the paradox. And then in 1955, there was another logician, Arthur Pryor, from New Zealand, who he wrote a book called Formal Logic, and he said that that every sentence. It was kind of a similar resolution to Tarski's. He says that every sentence implicitly implies its own truth. I mean, you wouldn't have a sentence that, I mean, if you make any statement about the world, you're implicitly assuming that statement's true, obviously, because a statement's a statement. It's telling you something about the world, and it's not telling you that it's wrong. It's telling you something that you're assuming is right. So if you have a sentence like this sentence is false, that sentence is it's like saying A and not A. If the sentence is A, then this is basically A and not A, which is according to Aristotle's law of excluded middle, that's not that's a contradiction, a logical contradiction, and allow those. So that's kind of another way to resolve this paradox. And then the third way, I kind of like this one the best. There was another form of logic that was, I think it was first developed in the 1920s, but it was fully developed in the 1960s. It's known as fuzzy logic. And I actually like fuzzy logic. I may do another video on it, but actually, I haven't made a video on it yet. I may do a video on fuzzy logic because I think it's a lot of fun and it's very useful as well. And according to fuzzy logic, what differs from fuzzy logic and what's called classical logic, in classical logic, every sentence or every statement has a truth value of either 0 or 1, 0 being false and 1 being true. And of course, you get a contradiction if you assume that the sentence "I am lying" or the sentence is false. If you try to assume that sentence has a truth value, there's 0 or 1, you get a contradiction. Uh, we've already established that. But if in fuzzy logic, sentences can have truth values anywhere between 0 and 1, any real value from 0 to 1. So in particular, they can have a truth value of 1/2. And it turns out the negation of any sense in fuzzy logic, the truth value, if the truth value of the original sense is x, or x is some real number from 0 to 1, then its negation has a truth value of 1 minus x. So if you assign the sentence "I am lying" a truth value of 1/2, or 0.5 if you like, then there's no contradiction. Its negation also has a truth value of 0.5, and they both kind of say the same thing. They're really kind of both the same sense in disguise. So there's no problem if you assign a truth value of 1/2. It's another way to resolve this paradox. Anyway, that's pretty much all I have to say about the liar paradox. Thank you for watching. Long live math, and I'll see you guys next time.